Welcome back to the lectures on existence and uniqueness of solutions of initial value problems. We have discussed about the Lipschitz continuity of a function of two variables, and also we proved in the last lecture the Grunwald's lemma, which will be used in proving the uniqueness of solution of an initial value problem. Let us recall the Grunwald's inequality which we did yesterday. The Grunwald's inequality, recall Grunwald's inequality or Grunwald's lemma. So, let fx and gx be two real valued function be two real valued function defined on some interval a b such that both fx and gx are non-negative on the interval a b. Then the inequality fx is less than or equal to c plus integral a to x ft gt dt with a constant k times, where c and k are positive constants, implies, then this inequality implies fx is less than or equal to c times e to the power integral a to x k gt dt for x in the interval a b. So, this inequality says if whenever we have an inequality fx is less than or equal to c plus integral a to b k times ft gt, that implies that fx is less than or equal to c times this constant c times exponential of the integral a to x k into gt dt. The advantage of this inequality is that in the first inequality fx is coming on both sides, and the second inequality gives a bound for the function f. The right hand side is independent of f. And a special case of this Grunwald's inequality we will use in proving the uniqueness theorem. So, that I state as a corollary let fx be a real valued and non-negative function, negative continuous function, defined on AB in the ground-Walsh inequality also we require fx and gx be two real valued continuous function. There also continuity is required for giving a meaning to the integral. So here the corollary, let fx be a real valued and a non-negative continuous function defined on AB, and k be a constant. Then the inequality fx is less than or equal to integral a to x k times ft dt implies fx is equal to 0 on the interval a to b. So this is a special case of ground-Walsh inequality where the constant c is 0, and gt or gx is 1, but c we assume to be a strictly positive, is a strictly greater than 0, but that can be tackled. Okay, let us see a proof of it. Proof of corollary. Let epsilon greater than 0 be a given number. Let epsilon be an arbitrary number given. Now consider the inequality. Consider the inequality. Fx is less than or equal to epsilon plus integral a to x k times ft dt integral a to x k times ft dt. Now fx is a continuous non-negative function and k is already given. K is a positive constant, strictly positive constant, and epsilon is strictly positive. Now by applying ground-Walsh inequality on this, so by applying ground-Walsh lemma with, so remember ground-Walsh lemma is fx is, whenever fx is less than or equal to c plus integral a to x k into ft gt dt, we have the inequality fx is less than or equal to c times exponential of the integral a to x k into gt dt. So, if you apply this Grunwald's inequality here with gx is equal to 1 and c is epsilon, which is of course greater than 0, then we get f of x is less than or equal to c times, c is epsilon times e to the power integral k times integral a to x k times g is 1. So, this is k into dt, which is equal to epsilon e to the power, if you integrate x minus k times x minus a. So, therefore, this implies that this function, non-negative function f(x) is less than or equal to epsilon times e to the power k, and x varies from a to b. So, the upper bound is b minus a. So, e to the power b minus a is a finite quantity, and this is true for all epsilon, any given epsilon. So, since epsilon is arbitrary and fx is greater than or equal to 0, we have fx is identically 0. So, this quantity is a finite quantity, and this is true for all epsilon, and f is non-negative. So, implies that fx is equal to literally 0. So, this form of Grunwald's lemma we will apply in the uniqueness result. Okay, let us consider the come to the uniqueness result. So, consider the initial value problem. So, dy by dx is equal to f of x comma y with the given initial condition y at x0 is y0. So, this is the initial value problem, and we will prove that if f is Lipschitz continuous with respect to x, then the solution of this initial value problem is unique. So, by making use of the Lipschitz continuity condition, we will prove that the uniqueness of result, and also we will invoke the Grunwald's lemma. So, tools, so Lipschitz condition, Lipschitz continuity of f with respect to y, and Grunwald's lemma. So, we will also invoke a basic lemma for the initial value problem, a basic lemma for the initial value problem. Okay, let me state and prove a basic lemma for the initial value problem. If yx is a solution if Yx is a solution of the initial value problem, dy by dx is equal to f of x y and y at x0 is y0, then y satisfies the following Volterra integral equation. Volterra integral equation. It's given by y of x is equal to y0 plus integral x0 to x f of t y of t dt. So, this is the integral equation. We denote this by IE, and the initial value problem is IVP. So, the basic lemma is if y is a solution of the initial value problem, then y satisfies the Volterra integral equation yx is equal to y0 plus integral x0 to x f of t y t dt, and conversely if y is a solution of the integral equation IE and y belongs to the class of all continuously differentiable function defined on some interval x0 x1 with x1 is some number greater than x0. So, it is a solution of the integral equation which is continuously differentiable on the interval x0 x1, then y satisfies the initial value problem. It means y is also a solution of the initial value problem. So, one way we are converting the problem of solution of the differential equation into the problem of the solution of an integral equation. And this integral equation, i.e., the solution of the integral equation can be treated separately. The solution of an integral equation need not be differentiable. In case it is differentiable, we can show that it is a solution of the initial value problem. So, the proof of this basic lemma proof so what we have is the differential equation dy by dx is equal to f of xy. Now, integrating with respect to x over an interval x0 to x, we get so integral x0 to x dy dx dx is equal to integral x0 to x f of we change the variable to t, and y is also a function of x, y of t dt. and this is y at x minus y at x0 is equal to integral x0 to x f of t yt dt. And we know that the initial condition y at x0 is y0. So therefore, and pushing this to the right hand side, y of x is equal to y0 plus integral x0 to x f of t y of t dt. So this is a integral equation, Volterra integral equation. So therefore, if y is a solution to the initial value problem, then y satisfies the integral equation. Now we will prove the other way. Suppose that y is a solution to this integral equation, or y satisfies this integral equation, and y is also continuously differentiable, then we can so suppose y is in C1 x0 x x1 and y satisfies IE, then differentiating with respect to x, differentiating with respect to x, we obtain so dy by dx is equal to derivative of y0 is 0 plus now d by dx of integral x0 to x f of t y of t dt, using the Leibniz rule for differentiating an integral. So we get this turns out to be f of x y of x. So the derivative of this integral is derivative of this integral is f of x y of x. So therefore we get dy by dx is equal to f of x y of x. So therefore the function satisfies the differential equation, and it's very easy to verify that y at x0 for the integral equation. See, in this integral equation, if you look at the integral equation, and if you substitute, if you replace x by x0, if you replace x by x0, then this is integral x0 to x0, that's vanishes, and y at x0 is y0. So obviously y at x0 is y0. So this implies that y satisfies the initial value problem. Now, as I pointed out, a remark. So one can study solutions of the integral equation without differentiability assumption, without differentiability assumptions on y, but only with only with continuity assumption. Continuity assumption on y. So such solutions are known as mild solution. Mild solutions or weak solutions. Of the initial value problem. So if we don't require the differentiability condition on y, then the solutions of the integral equation, Volta integral equation just defined, are known as mild solutions or weak solutions. Now we are ready to prove the uniqueness result. So theorem. We now state and prove the uniqueness theorem for the initial value problem. Suppose that f of x y is continuous, f of x y is continuous, and Lipschitz continuous, with respect to y on a rectangle R which is in R2, where R is defined as R is a rectangle set of all x y such that x minus x0 is less than or equal to a, y minus y0 is less than or equal to b for some constants a and b positive. So we assume that, suppose that f is a continuous and Lipschitz continuous with respect to y on a rectangle R, and the rectangle is defined this way with Lipschitz constant with the Lipschitz constant alpha, then the initial value problem dy by dx is equal to f of x y, y at x0 is y0, then the initial value problem, when we say then the solution, then the solution of the initial value problem is unique. If it has solution, then the solution is unique. But because of the continuity, continuity is assumed with respect to both x and y. Because of the continuity, there exists a solution, and here our major emphasis is on the uniqueness, and since f is Lipschitz continuous with respect to y, we are going to prove that the solution is going to be unique. So, if solution exists, then the solution is unique. It cannot have more than one solution if f is Lipschitz continuous with respect to y. Okay, we will prove it. The proof we invoke the Grunwald's lemma. So, let us assume that it has got two solutions. Let y of x and z of x be two solutions. Let y and z be two solutions of the initial value problem. Defined on some interval x0, x1. So, thus by the basic lemma, basic lemma says any solution that is satisfying the initial value problem will also satisfy the integral equation. So, basic lemma says a solution satisfying the initial value problem, will also satisfy the integral equation. So, therefore, we are using the basic lemma. So, thus by the basic lemma, yx is equal to y0 plus integral x0 to x f of t y of t dt, and similarly z is a solution. So, zx is equal to y0 plus integral x0 to x f of t zt dt is also a solution. Now, subtracting one from the other one. So, subtracting we get yx minus zx is equal to y0 and y0 get cancelled, and the integration domain of integration is common. So, integral x0 to x f of t yt minus f of t zt dt. Now, if you take the absolute value y of x minus z of x is less than or equal to integral x0 to x absolute value of f of t yt minus f of t zt dt. Now, we have assumed that f is Lipschitz continuous with respect to the second argument y. So, f is Lipschitz continuous with respect to the second argument. So, therefore, we can use a Lipschitz condition or Lipschitz continuity. So, this is less than or equal to. So, by Lipschitz continuous. Alpha times integral x0 to x y of t minus z of t dt. Okay, this is by the Lipschitz continuity, by Lipschitz continuity. of f. So now we have an inequality that absolute value of yx minus zx is less than or equal to alpha times integral x0 to x absolute value of yt minus zt dt. So now if we use the corollary of Grunwald's lemma, see the corollary of Grunwald's lemma, if you have a situation like this, if fx is less than or equal to integral a to x, so if f is less than or equal to integral a to x k ft dt, then fx has to be 0. Here the conditions on f is non-negative, continuous, and k is a positive constant. So if this the conclusion is ft is equal to 0. So if we come to our inequality, so now by using Grunwald's, so we obtained that absolute value of y of x minus z of x is less than or equal to integral x0 to x alpha times y of t minus z of t dt. So applying Grunwald's inequality, Grunwald's lemma with, so Grunwald's lemma, we use a corollary with f of x is absolute value of y of x minus z of x, and k is equal to alpha, and gx, the corollary is 1, and c is 0. So we get f of x is literally 0. So that is yx minus zx is equal to 0 for x in the interval x0 to x1. So the conclusion is, so this implies that, so we started with two solutions y and z, and we have come to a conclusion that the difference between these two solutions for all x is 0. So that is y of x is equal to z of x, proving the uniqueness of solution. So the solution is unique. Now we will consider a few examples. So example, call it example 1, dy by dx is equal to y plus exponential 2x with initial condition y at 0 is 2. So look at this simple initial value problem. See, note that it is a linear differential equation. It's a linear differential equation and non-homogeneous, So, linear and non-homogeneous differential equation, and this equation is first order. So, sufficient theory has already been developed, and you have seen how to solve this equation by using the method, using the integrating factor techniques and all. So, let us analyze the solution, existence of solution, uniqueness of solution. Okay, here the function f of x y, the right hand side is of this equation is y plus e to the power 2x, and this is continuous. So, with respect to x and y, it is a linear in y and is an exponential function in x, is a continuous function, the all R2. So, f is continuous. And what about the Lipschitz continuity? So, f of x y1 minus f of x y2, which is equal to y1 minus y2. So, it is linear. So, therefore, it is obviously Lipschitz continuous. Okay, it is Lipschitz continuous. Here the Lipschitz constant alpha is 1. So, it satisfies all the conditions of the uniqueness theorem. So, the function is continuous in x and y, and the function is Lipschitz continuous with respect to y with the Lipschitz constant 1. So, therefore, by the uniqueness theorem, so by the uniqueness theorem, okay, the IVP, this initial value problem, has a unique solution. This linear problem has a unique solution. Remember that not all linear problems, linear initial value problems are having unique solutions. We have seen examples, and further we will see examples. And by using the integrating factor and the method which you have already seen, we have seen that a solution of this equation is given by y of x is equal to e to the power x, by applying the initial conditions, e to the power x plus e to the power 2x is the only solution. This solution is found by using the method we studied earlier, and by the uniqueness theorem, this is only solution. And now let us consider another example. So, example 2. So, let us consider a nonlinear initial value problem. So, consider a nonlinear initial value problem given by dy by dx is equal to x into sin y, where this function is defined on for x on a domain. Domain is defined by set of all x y, where x is bounded by 2 and y is free. So, y is varying from minus infinity to plus infinity, and x is bounded by 2. So, let the initial condition be y at 0 is 1. we will analyze the existence and uniqueness. So, first let us write down the function. The right hand side function f of xy is x into sin y is continuous on D, and we will check whether this function is Lipschitz continuous with respect to the second argument y. To check the Lipschitz continuity of f with respect to y, we have stated and proved a sufficient condition. If the partial derivative of f with respect to y is bounded in the given domain, then the function is Lipschitz continuous with respect to y in that domain. So, the partial derivative, so del f by del y is equal to x cos y, and if we take the bound, say you take supremum of this one for all x y in D, so this is even maximum is enough, so maximum is attained. So, x y in D, so this is equal to cos y is bounded by 1 and x is bounded by 2. So, the supremum is 2. So, therefore, this implies that x sin y is Lipschitz continuous on D with respect to y with Lipschitz constant, with the Lipschitz constant alpha is equal to 2. So, therefore, this function satisfies all the conditions of the uniqueness result. So, f satisfies conditions of uniqueness theorem. So, this therefore, the conclusion is, so dy by dx is equal to x sin y with y at 0 is 1 has a unique solution. A unique solution starting from the given point 0 1. But the existence part, as I have already mentioned, if the function is continuous with respect to x and y, then existence is guaranteed in some interval starting from the given initial point 0 1. And now what we have proved or observed is the uniqueness is guaranteed because of the Lipschitz continuity property of f with respect to y. Now, we will see an example where we have more than one solution. That example we had already seen a linear equation. So, take an example. So, example 3. So, consider the initial value problem. Of course, this is a linear one, dy by dx is equal to 2 by x into y, and the initial condition y at 0 is 0. So, in our earlier sessions we have obtained its general solution and also its solution satisfying the initial condition. So, note that y is equal to c into x square is a solution for the initial value problem for every value of c. So, therefore, it has got, we have seen that it has got infinitely many solutions. Let us just check why or how we compare this with the uniqueness result. So, in this case f of x y is 2 by x into y on an interval say 0 to some number, say 0 to 2. 0 is a point given, and del f by del y obviously it exists, is 2 by x. But if we take the supremum of del f by del y when x and y, or here depends only on x, when x is in the interval say 0 1, which is sup so this does not exist. We know that this blows up. So, therefore, the function f is not Lipschitz continuous. With respect to y. See, at x is equal to 0, you see the singularity is there for this differential equation. As x goes to 0, 2 upon x blows up. So, if it is not Lipschitz continuous with respect to y, so therefore, there is no surprise why this equation does not have a unique solution. So, the uniqueness theorem does not apply here. So, uniqueness theorem does not apply here. And we have several other examples which we dealt with. One example which can be done as an exercise. So, example 4. So, consider the initial value problem dy by dx is equal to 3 y to the power 2 by 3. The initial condition y at 0 is 0. We have seen in the earlier lecture that this equation, this differential equation has got infinitely many solutions, including yx is equal to x cube. So, it has got many solutions, and in this case also, if we look at the function f of x y is equal to 3y 2 by 3. So, it is a continuous with respect to both the arguments, but it is not Lipschitz, is not Lipschitz with respect to y, on any domain containing the point 0 0. So, not Lipschitz on any domain containing 0 0. So, therefore, the uniqueness is not assured by the uniqueness theorem. Okay, so, given a differential equation, we can make out whether the equation has a unique solution provided the function f is Lipschitz continuous with respect to y. That is one of the sufficient conditions. Again, remember, it is not necessary. There can be a function which does not satisfy Lipschitz continuity, but still thus it can have a unique solution. And we will prove the existence theorem in the coming lectures. So, by various existence theorems we will see. Okay.